There's a cosmic monster out there, so powerful that nothing can escape its grasp. It's called a black hole. But here's a strange mystery. Scientists say information in the universe is never lost. Yet, when something enters a black hole, it seems to vanish forever. This bizarre contradiction has sparked one of the greatest scientific battles of the century. On one side, quantum laws scream, "Information must survive." On the other, black holes act like cosmic vacuum cleaners, sucking everything in. So, what's the truth? Where does the information that enters a black hole go? Is it destroyed? Hidden somewhere in the cosmos? Or perhaps stored in some weird way? This is the black hole information paradox, a grand mystery that might hold the key to unraveling the secrets of existence. In this video, we're diving deep into this enigma. From Einstein's and Hawking's theories to today's mind-blowing ideas, we'll explore it all in simple terms. So, buckle up, because we're about to embark on a cosmic adventure that might just flip your view of the universe. Let's start from the basics. Black holes are some of the strangest phenomena in the cosmos. They form when a massive star, say dozens of times larger than our Sun, reaches the end of its life. When its nuclear fuel runs out, it can no longer resist its own immense gravity. The core starts collapsing, triggering a massive explosion called a supernova. If what remains is heavy enough, it collapses into an incredibly dense point called a singularity. Around this singularity forms an invisible boundary, the event horizon. This boundary is like a one-way wall. Anything that crosses it, even light, can never escape. That's why we call it a black hole. It emits no light, appearing as a vast shadow in the cosmos. Now imagine a spaceship approaching a black hole. What happens to it? According to Einstein's general relativity, introduced in 1915, black holes challenge the very laws of space and time. If a spaceship crosses the event horizon, to an outside observer, time for that spaceship slows down, and slows down even more. It might even look like the spaceship never fully crosses the horizon. But from the perspective of the spaceship's crew, everything feels normal. They pass through the event horizon and head toward the singularity, where gravity is so intense that the laws of classical physics break down. This singularity is a mysterious point. Its density is infinite, and general relativity can't tell us what happens there. It's as if the cosmos pulls a black curtain over our eyes and says, "This far and no further." According to relativity, information that enters a black hole seems lost to our world forever. But is it really gone? Here's where a big problem arises: the information paradox. Before we tackle the paradox, let's clarify what information means in physics. In everyday life, information might be a text, an audio file, or a photo. But in physics, especially quantum mechanics, information refers to all the properties of a physical system. For example, take a proton. Its information includes things like its mass, electric charge, speed, position, and even a weird property called spin. These properties are stored in something called a quantum state, a sort of cosmic DNA that defines what a particle is and what it will do. There's a crucial rule in quantum mechanics called unitarity. It says information is never destroyed. Even if a system falls apart, its information persists in the universe somehow. For instance, if you burn a book, its information lives on in the smoke, ash, and heat released. This principle is sacred to physicists because if information were lost, quantum predictions would collapse. So, here's the question. If an object enters a black hole, what happens to its information? Relativity says it's gone for good, but quantum mechanics insists it must be somewhere. This conflict is what creates the information paradox. Imagine a spaceship filled with scientific books and human data approaching a black hole. To an outside observer, the spaceship never fully crosses the event horizon because time slows down for it. But from its own perspective, it zooms toward the singularity. Here's the question: what happens to the information in those books? According to general relativity, it seems to vanish into the singularity. But quantum mechanics says information can't be destroyed. This creates a huge clash between two of physics' most trusted theories. This paradox was first raised by Stephen Hawking in the 1970s. He argued that if information is truly lost in a black hole, it violates the principle of information conservation, a disaster for quantum mechanics. But if it's not lost, then where does it go? This question has driven scientists to search for answers for decades. In 1974, Stephen Hawking made a shocking discovery that changed how we view black holes. They're not completely black. They leak energy through something called Hawking radiation. Here's how it works. In the quantum world, empty space isn't really empty. It's buzzing with virtual particles and antiparticles that pop into existence and annihilate each other instantly. If this happens near a black hole's event horizon, one particle might get trapped inside while the other escapes. The escaping particle appears as real, making it seem like the black hole is radiating. This radiation comes at a cost. The black hole loses mass over time. If nothing feeds it, it could evaporate completely. But here's the problem. Hawking initially thought this radiation was random, carrying no information about what the black hole swallowed. If that's true, the information is lost forever. But physicists like Leonard Susskind and Gerard 't Hooft argued, no way. The information must be in the radiation, perhaps encoded in some mysterious way. One of the most fascinating ideas to solve this paradox is the holographic principle. It suggests that information entering a black hole isn't lost in the singularity, but is stored on the event horizon's surface in a two-dimensional form, like storing a 3D movie on a flat screen. This idea began with Jacob Bekenstein and Hawking, who showed that a black hole's entropy, its capacity to store information, depends on the area of its event horizon, not its volume. A major step forward came in 1997 with Juan Maldacena's AD-SCFT theory. It proposes that a multidimensional gravitational universe could be equivalent to a quantum system on its boundary. In other words, our entire universe might be a hologram, with all its information written on a 2D surface. This idea isn't fully proven, but it has strong mathematical backing and explains many physics puzzles. In recent years, scientists have made huge strides towards solving the information paradox. One new idea is quantum islands. What are they? Picture a black hole as a cosmic safe, storing information in specific regions. These regions, discovered through complex mathematical calculations, can preserve the information of everything the black hole has swallowed. As the black hole evaporates, This information leaks out through Hawking radiation. Another idea is quantum hair, proposed by Hawking and colleagues like Andrew Strominger. These are tiny, low-energy patterns on the event horizon that can store information. In 2021 and 2022, papers in Physical Review Letters showed that these hairs might be the key to solving the paradox. Through quantum entanglement, a weird connection between particles, this information is transferred to Hawking radiation, ensuring nothing is lost forever. All these ideas, from Hawking radiation to quantum islands, might just be pieces of a larger puzzle. Quantum gravity. This theory aims to reconcile general relativity, which explains the large-scale universe, with quantum mechanics, which governs the subatomic world. These two theories work beautifully in normal conditions, but in extreme cases, like the center of a black hole or the Big Bang, they seem to fight. Some believe string theory or loop quantum gravity could be the ultimate answer, but we're still a long way from a complete theory. Solving the information paradox might be the key to unlocking a theory that explains the entire cosmos. Black holes aren't just astronomical objects. They're like cosmic laboratories testing the fundamental laws of existence. The information paradox hasn't been fully solved yet, but every step scientists take brings us closer to the truth. Maybe one day we'll discover that black holes don't destroy information, but act as vast cosmic libraries, telling the story of the entire universe.